on Twitter, see if we're actually live. And whoever has the EthVan Twitter. Discord's got it. And boom, okay. And all right, Radney, you can probably get into the driver's seat.
Okay, just give me a sec. So it's...
All right. Do you want to sit or are you standing?
I prefer to stand.
Okay, well then let's get rid of that.
It's too heavy though.
You have to stand there. Otherwise, you're not going to be standing here.
Okay. Is it good now?
There, let's see you. All right, go back into the camera.
There you go,
Yeah,
Oh, it's
that'll
too
work.
far though.
We'll tweak it up a little bit here. We're gonna
Yeah,
do
like
it live.
you're good there.
Yeah, that one is better.
Just a moment here, folks. Whoa.
Yeah, it's too...
Yeah, let me get back to OBS. There. All right. Yeah, that'll work, Radney. It's a little bit off. Actually, hold on. There, that way we've got the screen out. Okay. All right, thanks everybody for coming. A few familiar faces here tonight, and yeah, I don't think everybody's already joined all the socials, so that's cool. There's a PO app tonight. If you want it, tap it. Please do that. Go through all the work of making them. Please go claim them. Yeah, Radney's here tonight to talk about mitigating toxic MEV. This is a deep one, so for anybody that you're about to learn some pretty deep stuff here. So yeah, with no further ado, Radney, please take it away.
Okay. Hello. So, yep, it's Radney. People call me Radney. You can say so. And then I'm into space since like 2017 or so, like deeply. Oh, that way. Okay, sorry. I was mostly focused on cryptography side of the thing, and I'm doing research in cryptography. And this thing that I put here is basically the result of my like probably a year or so of research. And then if you don't know anything about what does that mean, just bear with me. It's okay. We'll go over it. Yep. Let's start it. So, because I can see like so many new faces tonight. How many of you have no idea what's blockchain? Just please raise your hand. Okay. No one. Awesome. And how many of you don't know anything about MEV? So basically no one knows anything about MEV. Probably. No worries. It's okay. But I actually like already provided some slides to give you some like background knowledge about what is happening and what does those terms mean in detail. But let's start with blockchain, and then as we all already know, that's like the chain of blocks. I don't really spend that much time on that. You just add like transactions, which are basically like mostly financial information, and then we just like block them up together and create new blocks, and then the reference to the last block via these like hash functions, just like basically preserve the like tamperness of the thing. So you cannot change anything on the old blocks, and then because the result will be propagated to the new blocks. So this like blockchain thing abstractly provided so many new things and so many cool things in the financial system, which we call it like DeFi. It's like new generation of financial system. But at the same time, it also introduces many new types of attacks that we really don't like them. And among those attacks, I'm pretty sure like all of you probably have heard about flash loans and stuff like that, that people just one single transaction made like millions of dollars just by just stealing money from other people. But still, even though we have those kind of attacks, the most probably like dangerous ones is this MEV thing. And so to just give you a rough idea of what is that, because like this blockchain thing is super transparent, and everything and everyone in this world is capable of watching what is happening just on time and like live. And so when you send your transactions, when you're interacting with the system, then everyone else is also observing what you're doing, and so they can take advantage of that and then do whatever they want right before or after you, and so that way they can make so much money, and at the same time you will lose like terribly high like very big amount of money. So this MEV thing can like include many like different instances, like front running, back running stuff. But then, just to give you some idea, let's explain what is front running if you're not familiar with that. Basically, like this front running term has already existed in traditional finance. As you might guess, it just changes variation so that in this new model, it's relatively the same thing, but with like a little bit different. Here I just provided an example of this front running. Assume like Alice is our good user here, and they want to exchange some ether, buy some ether via USDC. So for those of you who don't know what is USDC, USDC is like a token in blockchain space who is pegged to, assumably pegged to $1. It have to like retain the $1 value no matter what. And what is Ether? Ether is the native token on Ethereum blockchain. And recently people say that it is also pegged to $2,000. Just no offense. So this Alice basically wants to buy 1K ETH with as less USDC as he can, because ideally that's his financial profit. And then she just basically sent her transaction to the mempool. What's mempool? Mempool is like a place that you just basically send your transaction. Transactions will probably stay there and wait for the miner to pick them up and then execute them through some like mechanism. We don't care about that. And so, okay. So Alice sends a transaction to the miners, and then because like it's an open place, it's like this space is open to everyone. And what the other people can do along with the miners, they basically can, as they're watching the transaction, they can create another transaction and put their own transaction right before Alice's transaction, and they basically can front run Alice's transaction in that way. So what happens is that the miner can basically buy as much ETH as they can right before Alice's transaction, and so the price of ETH will go high, super high, and then at the time that Alice is buying that ETH, they are again like increasing the Ether price in value, and so eventually the miner end up with making so much profit out of that, and that's Alice who lost so much money because of that. So yep, that was just one example to just show you how does the system work when we have like this opportunity. There are like back-running sandwich attacks, PGA, as you probably have heard about that one. It was like probably the first thing that the community get to know about when Flash Boys started to like working on this thing. But still, it's not just the users who matter in this system. For developers, to be honest, they don't really care that much about that specific user lost $100 or like $10. They don't really care. But the situation can be even worse than that. What do I mean by that? It's like the previous example that I showed you. Alice sends a transaction, and then the transaction get into the block. The block miner fronts run Alice. But now assume like after 2 blocks, we surprisingly see another fork of a network that has been created with another miner based off the head of that block. And so why did that happen? Because like that miner realizes that there was a front-running opportunity back in the day in one of the old blocks. And so they want to kind of like steal that profit from the other miner. And so because of that, they will create a fork on top of that block to just basically like take advantage of the exploit. So as you could see, it's not just users who are in danger. The entire consensus mechanism is now kind of like super annoying right now. We have really no way to just confidently say that this block is finalized, because like many people could just thrive, do their best, to steal those opportunities because of that like single MEV threat that lies in that block. And unfortunately, even like few years ago, it is like for Flashboy's initial paper, they show that this thing is already there, like this much of profit, because like miners have to pay something in order to make that fork successful. And they actually showed that the money is already there, and the miners even at the moment are kind of like incentivized to do that. So it's a like serious challenge for all of us right now, and especially for Ethereum communities. So like Ethereum Foundation is paying millions of dollars to just prevent that from happening. And basically, yeah, as I mentioned, like by removing this possibility, this like toxic MEV that we call it, special thanks to Sufi, Steph, sorry. If you like just get rid of that, it's good for all of us. Okay, so it was just some background knowledge about what's that and why does it matter. But then the reason why we generally came here is what's the solution? There are basically arbitrarily many solutions that people are talking about these days, especially like recently this topic has become like super hot for people. But tonight I'm going to tell you one, like my approach. It's not like inclusive for me, but the whole idea is just basically many people have that. Separating the inclusion and execution of transactions. And I will tell you what does that mean the next few slides. So let's look at the system, like how is the system right now? The current model, users just create the transactions, they are plain text. They just broadcast transaction to the network, get into the mempool, and so at this moment, everyone knows what's the content of transaction that we mentioned. And then the miner choose the transactions from the mempool, create the blocks based on those, and right after that, execute the transactions according to the order that they predetermined. So as we already saw, there's an MEV risk right here. But now this time, let's assume this new model where users, instead of sending plain text transactions, they encrypt the transactions and then they broadcast it. Now no one, absolutely no one other than the user has any idea what is the content of these transactions because they're encrypted. So what miners should do is to this time, they have to choose, they have to create the block transactions with the encrypted ones so that potentially, like, assumably they have no idea what are they doing. They're just picking the transaction from mempool and putting it in the block. And then the transactions, once they get into the block, after let's say like few moments, few like minutes, I don't know, whatever, they get decrypted, and then that's a moment where the miners execute the transactions. So hope it's clear to you that it is kind of like MEV safe. There are like theoretical proofs that you can prove that claim, but I hope like everyone is with me and they agree that it is kind of like MEV safe. Yeah.
Quick question. So in this model, it would just be fee priority for transactions, or what happens?
Yep.
Yes. Okay.
It's gonna be fee priority. I mean, it depends on the network decision. They can choose, but you know, to be honest, you can also like hide fee as well.
Sure, but
That's
yeah,
possible.
in this, if you don't know what's in the transactions, right? You're just like, okay, well, what edge do I have? So the edge would be not even edge, but just like, why am I actually going to include these transactions? Okay,
so like basically, ideally, what we really want is based on first come, first serve.
Got it.
Like,
okay.
You know, that's basically like, I think it's the best case.
Okay.
Yeah.
Are there difficulties with first come, first serve though? Like in the sense that it's hard with like so many different transactions coming from so many different places, like which one actually came first, like all the timing of that?
So, by first come, first serve, what I meant was that, yeah, definitely we cannot make any assumption based on the time that the transaction came. But if you don't know what is the content of the transaction, and also you don't know what is the fee of this transaction, then what would you do? You would just basically put the first one in the first, and then the second, and just go to the end. So basically, like, that's inherently what happens. But sure, like, you can choose whatever different ordering that you want. but you have no advantage or you have no incentive to do that. So that's why I'm saying like it's gonna be like one step further towards being first come first serve. Also, Julian. Yeah.
So in this model, wouldn't it make the blockchain more computationally heavy if you're encrypting everything?
There are like some implementation challenges. I'll mention that later, but in the thing that I built, there is kind of that's not a challenge. It depends on the underlying math. Yeah, go ahead. Can you use the mic?
Oh, yeah, sure. Where's the key for the encryption coming
Yeah,
from?
just bear with me. I'll mention that later. Okay. Anyone else? Is it okay? Okay. So moving forward, it's really easy to say that, as you mentioned, like there are multiple challenges in this new model, and I like highlighted two of them. One of them is, what does it mean to encrypt something? Who owns the public key? Who owns the private key? And how this encryption is kind of like happening? And then even more important is that we actually want the transaction to be decrypted. So who does that for us? Who does that for us? Like in terms of the transaction shouldn't be early decrypted, but still they should be decrypted. And so there are some like challenges that I hope like you understand like what's the issue here. Okay, so let's just put it simpler. Let's just get rid of blockchain stuff, and for the like next few slides I will use message and transaction interchangeably. I'm sorry for that, but that's it is what it is. So what we need is that we need to find a way to encrypt a message so that this message will be encrypted for probably like few minutes, I don't know, some predetermined time in future. And at the same time, it will definitely get decrypted. That's two important requirements that we need in order to be able to like make that whole like MEV safe system. So for that, we have three ways. The very obvious and naive way to do that is let's just ask people to commit to their messages and broadcast it, and then when we actually want the content, ask them to open the commitment for us. That's super easy. People do that, but then there is a drawback. What if the user doesn't do that? What if the user doesn't open the commitment? Then what do you do? Nothing. So that's definitely like not possible. It's just infeasible to use that. Second way, which many people have tried to use that, like probably Fairblock, I don't know. Let's assume that there is a committee here, that they are semi-trusted, and then those committee proposes some public key, and so the users would encrypt the transactions for the public key that those committee has access to, and then we can trust the committee so that after 10 days they will open up the commitment for us. Well, they will decrypt the message for us, or like after 2 blocks, after 3 blocks, I don't know, whatever. But then there is a like obviously trust issue here. Still, we need to trust some portion of the committee because they actually have to do that for us, and we don't like it, basically. There is a third way, which I love the most, and it's basically the reason why I ask all of you to come here. And that way, through that way, we are kind of like hiding the messages inside a mathematical object, and the underlying math kind of like guarantees to us that this message will be kept hidden until like this certain amount of time, and at the same time it gives us the guarantee that it will definitely get opened. So it also has some drawbacks. Everything in this world has some like limitations as well. I will mention those later, but even to this level, it should sound surprisingly to you that we actually have that in math. So basically, like the basic idea is time lock puzzles, and then they were introduced like in 1996. If you see with those like big heads, like Rivas and Shamir, I'm pretty sure that you have heard of his name before. But then it all boils down to the fact that they're using something called modular squaring, is assumed to be hard and unparallelizable. I will give you like some example to show you how the system is working. So just to give you an example, assume like here we have Alice and there we have Bob, and Alice wants to send a secret to Bob so that Bob has to wait until, I don't know, like few days in order to get the message. And so what Alice does is that Alice chooses a random number. It's a bit of math. Just feel free to just, I don't know, like to ignore it, but it's super easy. Alice has to just choose a random number, and then what she needs to do is to multiply the secret S with this random number 2 to the power of 1,000. But then, right now, just assume Alice has a magic wand that can do that super quickly, without any delay, no matter what, how. Just imagine that it's possible, and then passes over to the Bob. So how Bob can like take out the value of S out of P and R? Basically, they have to do the reverse of a thing. So he has to raise R to the power of 2 with 1,000, and he doesn't have that magic wand, and he eventually needs to just divide P over X and to get S out of that. Does that seem like legit to you? Is it okay? Okay. So that part, which I called it a bit like a few slides later, like modular squaring, that's where it comes to play, and it is assumed that it's non-parallelizable and it takes time. So you cannot, like, if when Bob has multiple processors, multiple CPUs or GPUs, it takes almost the same amount of time. That's how the system is working. Okay, so let's try to use this system. Let's try to apply that into our like MEV safe blockchain thing to see how the system is working then. So the obvious idea is to just ask people to put their transaction inside these like time block puzzles, and then they broadcast it to the network. So this way there is no party involved, there is no trust assumption, just everything goes by the math. But then there is one slight issue right here. What happens at the scale? Because I already mentioned that Bob needs to just keep the processor runs for like maybe 2 or 3 blocks for just one single transaction. And then what happens if 1,000 of transactions per block? Then the miner needs to probably like use thousands of threads at the same time running all together to just decrypt all the transactions of just one single block. That's not possible. So definitely that's not what's gonna happen. And for that problem, I came up with the idea of using what I call like this like delay encryption. It's not my idea. The delay encryption concept has been around since like 2 years ago. But then, let's just explain what's that. I just combined that with this like time block puzzle to build something new. Okay, for now, just assume like there is an oracle. We don't know who's that. That this oracle gives us an encryption key, which is public, and a decryption key, which is hidden inside a puzzle. And so, if you think about it, from now on, everyone can just encrypt the transactions for that public key, and then the transaction would remain encrypted till the time block puzzle is solved. And that's where we have access to the private key. Is there any question so far? Anything seem good? Okay. So these.
I do have one question.
Yeah.
So one question regarding the first option that you gave that seemed pretty decent is that the user actually commits with some sort of text, some sort of message, and I don't know if that's what you meant. That it operates like a salt for.
You mean the first option?
The first option, yeah, but back. This one.
This one, okay.
Yeah.
I mean, it's like user just hash the messages and then they send it.
Yeah, and there's no computational overhead because he's doing it at point of origin, right? He's doing it at his computer.
Yeah, sure.
So wouldn't that be solvable? And just, I don't know if you know what a pre-hook is, but if you don't do the message, you don't get to do the transaction. So why wouldn't this fly? Why is this a bad idea? I didn't get that.
because like, what if user just doesn't open the commitment?
So it doesn't open what?
The commitment, because like, as a miner, what
Yeah.
I can see is just the hash of the messages, hash of transactions. But then eventually we need the transactions itself to execute them, and then figure out what's the state of the network.
So couldn't he send deferably, like in a deferred way, the message to the miner? in
So
some
what
way?
if they don't? That's what I'm saying.
So the transaction fails?
So they can strategically fail
Yeah.
a transaction.
Absolutely, yeah.
That's not something that we want. And also that one, yeah.
Okay,
that's
so there are multiple problems on that. Yeah. Okay.
Remember, the message is the transaction, so it's like there's a broadcast, as I understand it. Rodney,
That's
you can
also
correct me,
correct.
but there's a broadcast, and then there's like this further interaction that would be required, and we're trying to only have it one.
I mean, yeah, that's true. Like, we cannot ensure that there is a like interactive interaction between those two parties. It's not possible. But at the same time, we don't really want some user to just abort the contribution to the network at the very last moment. Yeah. So, like for example, if that person is an MEV bot, they can send many like transactions, and then they can just don't reveal the content, and we don't really want that. And also like. Another probably like more understandable example is that just assume they are participating in a voting application. If anyone started to participating, they cannot have any way to hide the vote after they propose the vote. That's probably like the most sensible thing that you can think of. If you really want them to open up the commitment somehow. Okay, Steffi, no worry. Any other questions? So yeah, we are here. So basically, yeah, just assume like there is an oracle. They give us a public key and a private key hidden inside town like puzzle, and so everyone can just encrypt the transaction with that public key. So these two components along together, we have a mempool full of encrypted transactions, and a time like puzzle which just hides a decryption key, which is a secret key. And so later what happens is that whenever someone in the system like solves that puzzle, they will get access to the decryption key, and then all the transactions got like all together can be decrypted all at once without like kind of like no computational effort at that point on. So okay, let's just get into more details of that MD thing that I call it. How we kind of like create this system is that we have a setup phase, and in the setup phase, like we have this oracle gives us these two pieces of information, and then the encryption happens through like just usual encryption mechanism. We have a public key, and the message just encrypt the same way you usually do encryption. And the solve algorithm I probably will mention later, but there's a solve phase that miners probably have to do that for us. And then right after that, there's decryption. So, but now it just, let's just create the system for real. Like who plays the oracle right now? Because if we want to like trust someone as an oracle, then everything is just pointless for us. And as you probably might have guessed, let's just make it distributed as usual. So in the previous model, we had an oracle who does all the thing for us, but in this new model, we are asking many people to collaboratively create those pieces of information for us. I know like probably like your next question is, we already had that paradigm. We had like the second way, there was a committee who does the encryption and decryption stuff for us. But then you are also again introducing that committee to the system. What's the benefit of that? I will get to that point. No worries. I know that problem exists, but there's a solution for that. So this time we replaced that oracle part with something called the aggregate section, the aggregate phase, so that these like different people, they just propose shares through this generate algorithm, and then once we got all the shares, we do the aggregation, and then now we have access to everything that we need. So okay, so now we like reached the point to answer that question. Now we have like this system is kind of operating in a permissionless setting. everyone's welcome to participate in this generation. Can they actually attack the network somehow? So there are basically two ways that they can do that. One way is somehow they manage to like propose shares so that they end up finding the value of secret key before the predetermined time. So they can decrypt the messages earlier than anyone else. Is it something possible? But then assume like all the like these people here are adversary and they're colluding together to do that. Other than just one person. What we really want is that even in that scenario, they just all fail. So even if we have just one person who just acting honestly, this whole system can be just operate super secure. And that's what's the difference between this model and that second option that I mentioned like a few slides ago. There's also a second way that they can attack the system is that what if someone just uses a malformed share? You just input random shit into the system, and then what happens is that eventually everything just goes well, and at the end you will see that the decryption doesn't work because like they didn't give you a proper share to get into the like aggregate algorithm, and then at the end the message just doesn't decrypt well. Yeah.
I think I'm missing something, or maybe I just don't understand it correctly, but like at this point, right, like when you have the key shares that are being aggregated together to create the actual private key, you need a predefined threshold, right? So you need like, let's say there's 4 actors, and is it possible to create the key with only 3 of them? Is that how it works?
So how the system is working is that you basically just choose a high cap, 1,000, million,
Yeah.
10 million, and no matter how many of those 10 million shares are there, like as long as it's less than 10 million, the system works.
But up to a certain threshold, right? Like you can't just have like one key share. You need to
At
have
least
like
you need
at
to
least,
have like
2/3
one
of them.
honest person. And
Only
that
one honest one.
just one honest person.
Okay. So, oh, interesting. Okay.
So
Talk after.
no worries. Anyone else? Questions? Cool. So yeah, hope you understand. Like, if someone just inputs a corrupted share, then the decryption doesn't work at the end. So how to solve that problem? We are asking people to give us some proof that their share is actually not malformed, and we kind of can solve that problem as well. So yep, that was basically like 2 most important properties of the system: the correctness, which is the second one, and the security was the first one. Sorry, I just misplaced them, but it doesn't really matter. And I call the whole thing MDE. So I brought like a few math slides for those of you who are really interested to see like how the system is working. But as you can see, like this setup phase, there is a like that modular squaring operation that I mentioned like a few moments ago, like g to power of 2 power of t mod something. And then the gen algorithm, we're using that specific paper, like a combination of that. And then you see some people are just taking photos. You can, yeah. Okay. So you can check that out. And for the aggregate part, it's just basically simple multiplication, and that's it. There is no overhead. And the encryption decryption is happening through Elgamal crypto system, if you're familiar with that. So, and eventually the solve algorithm, you again need to do this modular scoring, like this thing. This is the last part. This one. Yeah. Do you know like Diffie-Hellman stuff? Do you know Diffie-Hellman stuff? Like, okay, basically like you have a public key, like this PK is a public in the system, and then if you want to encrypt something for the person, so you choose a random number R, and then you raise public key to the power of R, and here is a message that you actually want to encrypt with. So you do that, and then at the same time you provide G to power of R as the second piece, at the first piece of the ciphertext.
When you say message, you mean like
it's the
stats converted to base 64?
yeah. So you have like probably like a string or anything, like object. You convert it to like number, and then you do that. And so the decryption happens through like the C2, the second portion, divided by C1 to raise to the power of the SK. If you like do that by yourself, it's like it just all boils down to the fact that from having this thing, you have no way to find the value of R. It's called discrete log problem, like RSA, probably, if you have heard about. Okay, anyway, so the solve algorithm, also we have this like familiar operation here, it's modular squaring. And then I mentioned there is a verify thing that you need to make sure that the shares are not malformed. So that verify needs 2 steps. One of them is that you kind of like, with the second step, you have to make sure that it is not like the shape of the thing follows the protocol. And it happens via non-interactive zero knowledge proof, which again I used kind of the idea that these people used. I like adopted it with our system. And the first phase, the first like requirement is through some ZK snarks that we need to do exponent range proof of some public key that me and Owen were busy with like for a few weeks ago, I guess. It's actually like a really interesting question. You can try it by yourself if you want to. Yeah.
Create a proof for each transaction?
For each share, it's different. So okay, so as a user, you're just interacting with simple encryption decryption scheme, and that's it. You don't do anything other than that. But the committee that does that for us, they are kind of like doing some computation. But like, I would say like the most challenging part lies in this part, because as you increase the value of n, which is like the security parameter of the system, then this part becomes super like computationally heavy. It depends on the underlying like ZK snark protocol that you're using. And so probably like a mouthful way to explain all those things, this system can be proved to be secure and correct with having like these sort of like standard cryptographic assumptions. And also I provided some like charts to show you like how long does it take for the delay to take place. So for example, if you choose the n, like that big number, to has 4096 bits in length, and then if you like use these sort of like values, what happens is that for generation, it requires you to spend almost like 4.6 seconds, and for solving the thing, it takes like 24.3 seconds for like the miner to solve the whole thing. And then that's roughly like 2.5 time that you require to mine a block. And that's super like almost enough for all purpose, for like MEV purpose. Okay, so far we have solved like how the protocol abstractly would work, but then how we can implement that into the system, to the Ethereum network. So basically we need a committee of people to does that like generation algorithm for us. And then second, there are users who, instead of just sending transactions in plain text, they just encrypt that for us. And for miners, in this new model, they have to include the encrypted transactions and also at the same time execute the transactions which were included in one of the old blocks, and they were actually like encrypted. And so miners are now solving the puzzles. Whenever they solve a puzzle, they will try to decrypt all the transactions in that specific old block and then add the results of that into this new block. So we already know who are playing and what are the objective of the second and the third component of the protocol, but yet we don't know who is playing that part. And let's just recap some Ethereum background to see who is the right person who we can ask to do that for us. We don't really want to introduce new actors to the system. That's something we really want to avoid from happening. But anyways, like today's Ethereum, we have slots, and every slot is assigned with a block proposer, a validator to propose a block into that slot. And so for the other validators, what they're doing, they are kind of like attesting to the state of the network. And so there's like a station which works kind of like a vote. So people just vote which block is now the tip of the chain, and which fork of the network is the valid fork of the whole ledger. And also there is something called attestation committees. So it's basically per each slot of the network, we have 64 of these committees, and they kind of together create those attestation votes. We can always ask every single validator to give us some vote attestation, but that way we are excluding the network from with over probably 10 or 100,000 of attestations per slot. That's something that we really don't want to happen. So that's why we have attestation committees, and they are kind of grouped together to vote all together. So because of that, we have something called attestation aggregators that with high probability, we have one aggregator per committee. And so that aggregator task is that they get all the votes from every person in the committee, aggregate them together, and then propose one single attestation to the network. That's how today's Ethereum is working, actually. It's not something new. And just to let you know, that's also happening via this BLS signature. And again, this one is one of the magics that Ethereum brought via the merge, other than the proof of stake. So yeah, the design decision for our model is that we can ask the aggregators to do that as well for us. So along with that attestation, they will also create some shares, some time lock shares, and then propose the vote, the attestation object, to the block proposer to put it into the block. And then the block proposer would obviously aggregate all of those shares and create these slots public key. So I guess it's the last slide. I just wanted to show you how eventually the system will look like. That one, assume the block on the right is the current block, and then we have 3 blocks in the past. So the transactions of the current block are the encrypted transactions with the public key that was proposed by either of those blocks in the past. And obviously that block also executed some transactions of probably the 4th previous block, but we don't see the transaction there because there's no point to copy paste the transaction into the block. So they just has to decrypt the transactions of this block and then execute that and update the state accordingly. So, yep, that was all. Yeah.
Could you kind of explain the aggregation process a bit more? I didn't really.
So that's just simple multiplication over a few things.
But yeah, go back to the slide.
Oh, where was it? Yeah, this one.
Oh.
There are 4 different values. Okay, if you really want to know the math. So, no worries. This whole thing is just a time-like puzzle. There are 4 numbers eventually.
Yeah.
And the aggregation is just multiplying 4 values of each puzzle together, pairwise.
Okay. But so I want to encrypt my transaction, right? I go to this committee, the aggregation.
Oh, wait a second. You want to encrypt and you get in the committee?
Sorry?
I mean, if you want to encrypt, you don't need to be into the committee.
No, but I need to ask for the key, right?
So the block proposer already provided all the committee's share into the block. So you can see all the shares.
Okay.
So the public key is the multiplication of all those shares.
Okay, and it's one per block.
Yep.
Okay.
I mean, each block has its own shares, and definitely has its own final public key.
So you have 64 basically you have 64 committee members, right, who actually basically act as the oracle that gives you the key. What if one of them then is I will not tell you what my share was?
So if you don't provide the share, then I won't include your attestation into the block.
Yeah, but Yeah, but like at the start, first you commit your share, but don't you have to reveal the share later on? That like
Oh, you don't really need to reveal anything. There is no reveal phase at all. You just send your share and that's it.
you send your share, but then how does the decryption happen? So like, isn't there?
So, okay. Basically, like, as a committee member, you do this, which is
And-
like, you just generate some random things. It doesn't matter. And
Yeah.
also, you do the verify to show that this share is actually like well formed.
the share is well formed? Yeah.
Yep. And then
Once
As
you
a
have
miner-
64 well-formed shares, so then how does the miner like take the 64 well-formed shares and then use it to like decrypt it?
so the miner just picked all of them, put into the block, and then the future miners will start solving the share, the aggregated public key and the aggregated time block puzzle that was included in this block. So from now on, all the miners start to solve that puzzle, and
I
no
see.
one reveal anything. So just that's the whole point. Like, there is no need to reveal nor trusting someone to open up some commitment for us.
I see.
So, you're saying miners are solving puzzles of previous blocks in the
Yeah.
future. What if miners don't want to solve a block or a puzzle?
Their block will get failed. They have
But
to solve it.
They have to solve
Yeah.
the whole puzzle. Like, what if you want to submit a secret transaction or whatever, and then you are able to pay miners to not solve that block because your secret transaction's a flash loan attack?
So okay, that's like crypto economically, they will get punished, because like if the miner don't propose a block that they supposed to propose, then they will get slashed. It's even already
No,
there.
they're proposing the block, they just continue to delay the encryption.
Okay, so if they propose a block that doesn't solve the old block's time block puzzle, then the block is as if like they don't propose it. So that's the definition of a valid block. They have to solve the puzzle. But still, there are some the previous miner can still never mind. Let's just any more questions, because I don't really want to get into that point, because like I don't. In reality, we don't keep track of the verifications proofs into the blocks because they are big in size. We don't really put them into the blocks. We just ignore them, and we trust the miner that they actually verified the verification, like before putting it to the block. And if the decryption fails at any point, then that was the miner's problem, so we can punish them. That was just some side note. No worries.
So to provide the shares, you also need to provide this proof. I may have missed it, but what's the incentive to provide your share, or like a share?
What's in safe of what?
What's the incentive for the committee members to provide shares?
So as an attestation aggregator, you're doing your own task. If you don't provide a share, you don't attest to anything. So you already are incentivized to attest to the block. I mean, I am redefining the laws of the network.
Right. So it is added work, though,
Yep.
right? Yeah. Okay.
Can you go back to the table where you had like all the
Table? Okay.
where there's all the times? Yeah, so if you look at the modulus, which is 4096, why is the solve gen like lower? I'm at the end on the right side. So the solve.
Oh, the 5.28 you mean?
So what is solve?
Um,
What is solve slash gen?
I really didn't have enough time to get into that, why it's happening, because like it keeps decreasing, and it seems like the gen algorithm is kind of like getting more delay as you just increase the security parameter more than the solve algorithm. I don't know why is that, but then I kind of like stop here because I felt like okay, that last row is already enough for Ethereum, so we don't really care about the next. So that was kind of the rationale behind it.
Just a quick question: how you're planning to, at one point, implement this? Is this like going into a sort of fork, or?
It's definitely a hard fork for sure.
Okay.
Later, and also we already have implemented in some like testnet Ethereum, But in order to be fully operational, we are not solving MEV. Disclaimer. In order to be fully operational, it needs lots of more research, to be honest.
And second question is how would collusion happen between bad actors here? Shareholders.
So,
Can you give like a scenario of a feasible way of bad acting?
okay, assume like the miner of the current slot just received 10, I don't know, like 10 attestation aggregations. And among those 10, they know 3 of them. They can just drop the 7 other ones and use those. Yeah. I mean, they're all like all together, so they know each other.
So, yeah, a lot of that going on. So how do
Yeah.
you solve that?
Okay, so the point here is that you have to kind of like enforce the miners.
I mean, there could be a way that you would never, ever, ever know that is happening.
Yeah, sure. Okay, so the simplest way that you can like defend against that is to just ask the miners to have at least 30 attestation aggregators per block, and so
And then you
no,
pick-
they can pick randomly. You know, but because
Oh,
like
okay.
because like the random is too high. So
Yeah, absolutely.
yeah, that's
Cool.
basically
Wait, so when you say minor, you mean the block proposer,
the
right?
block proposal. Yeah, I'm sorry. Yeah.
I may have missed this, but all right. Let's say that within a block they're addressed by public key or something like this, right? It's not. There's not a there's not some extremely specific timestamp. What happens to encrypted messages, transactions that arrive that are not included in the block? Aren't they also able to be revealed later, which
Yeah,
you
that's
lose
correct.
privacy because we know what you were intending to include or propose, but now they're revealed because it's public
Yeah.
information. Am I misunderstanding that?
Yeah, that's a really good question. So, that's why I'm saying like there are lots of more research that needs to be happening before it's going to be like production. But then the point is that we don't let the miners to include the transactions that have been encrypted with more than like this amount of blocks, previous blocks, public keys. So they cannot use the stalled transactions at all. The block, if they use those, the block will become invalid. Does that make
But
sense?
we know something about the intent. Like that's what leaked.
So yeah, probably
I
like if
wonder
the
how
user
you
wants to
would
send another
solve that.
transaction, we will know that what is happening in this new transaction as well. But
Yeah.
they better to use different address for that, simply. I mean, it's not
No,
funny because like
that
we
works.
also can hide the address as well. So if they send a new transaction, you don't know that's kind of replicating the last one.
Yes, I like that. I like it.
Basically, like encrypting all the metadata of transactions is possible. I think, yeah.
Yeah, if you're hiding some metadata about it, I'm satisfied with that. So, you solved it. You just did the research on your feet.
Bro. Yeah. Go ahead.
Oh wait, so how would you hide the from address? Because don't you need to like verify that the transaction is valid before you like include
You
in
can
the
do
block?
it via ZK snarks.
So like more ZK.
More ZK. You can ask Alvin for that. Okay.
ZK is very like computationally centralized and heavy. So like, how do you manage that when like Ethereum's already expensive and slow? So you centralize it.
For that part, you're asking users to do that, not the Ethereum. Like
So then
miners.
if I have
I don't know
bad
honestly about that
laptop.
part. So because we didn't do that yet, and I'm just speculating that we are moving through a way that eventually all the metadata will get hidden from the outside.
but
It's
you're-
not just the concern of this project; it's the concern of all the other approaches as well.
But you're still kind of depending on the user to have a capable enough device to be able to process this, no?
Probably that process would become less computationally expensive in the future. I mean, that's not the concept of this fork. That's what I'm saying. So other folks are working on that. If they can do that, we can use that in the system and just attach it. Modularity, yeah.
So if you use something like Celestia for data availability,
Okay. Okay. Anything else? Yeah, go ahead.
First of all, fantastic, man. Awesome research. That was,
Welcome.
yeah, that's great. Does this also dive into solving censorship resistance within the network?
It does, absolutely.
So, like, yeah, Coinbase or something takes too much control, but at the end of the day, if everything is, you know, front to end, cryptographically secure within the mempool, I mean, there's no censoring of transactions going to be possible
Yeah,
if this were to
there
be
is no way
implemented.
because like it's just encrypted, and so actually like there are some other ways that other projects are doing. So like they kind of like enforcing the block proposer to solve MEV. They're enforcing block proposer to do randomization over the ordering, but via those ideas, the censorship can't be like prevented. And with this idea, like basically with encryption, you are guarding against censorship at all. Like just basically you just don't let anyone to know what's the content, and so what's the point of censoring anything we don't know the content? Anyone else? Yeah.
So with like Lido that has 33, or like 32, but in like 2 days when Blast gets another couple million, they're gonna have 33. Would that affect this if they have like so much control of the network for proposing blocks to like, even if everything is encrypted, but they can still kind of say yes or no to some encryptions or like delay stuff? Would that affect at all?
So
Like, would this solve Lido essentially?
I don't know about that one, but so
'Cause
if yeah.
Lido's validators aren't correlated necessarily, right? So it's like even though together they represent 33% of the network, like each individual operator they have, there's like 29 now, is only like a much like 1% each or something like that, and then so they wouldn't be able to like create a problem like that in that case.
In the case of Lido, like since they have like individual operators, like it's not like Lido as an entity controls what each of the operator does. So like there's not like an immediate problem in the first place that they can like all collude and like break the network. Yeah.
When it comes to like, let's say OFAC wants to get involved with transactions, and they're like, wait, you can't censor anything. So all of a sudden, if a like transaction that went through that was not OFAC compliant, what does that look like kind of on a, I guess, regulatory term?
You as a block proposer go to jail. I'm sorry.
That's, yeah. So, yeah, that, I don't know, that's just something that if someone, let's say, is in a jurisdiction that doesn't really favor towards OFAC compliant transactions, and then you just found out afterwards that you did provide a transaction to a, you know, sanctioned jurisdiction, that could be problematic.
So that's why I'm just on the research part of things.
Yeah, very good, very good. All right.
Yeah, it's a scale issue. If you like, do if you let an OFAC transaction in, sorry, it's a you problem.
Skill issues.
I got another question too, just regarding economic incentives. So you're saying MEV doesn't go away, and I can see how that is. But what is the incentive of all these MEV searchers now going to be if they don't know what kind of block they're going to be actually getting, you know, from MEV Boost? Or like, does MEV Boost and Flashbots even need to exist in this kind of scenario?
Yeah, they just disappear.
They disappear.
Yeah.
No, Flashbots now does intents. It's not MEV. It's intent matching. That is
Sorry,
the
you
future.
want to elaborate?
Yeah. So like, I mean, like, Flashbot started as like just like hey, like we can just let you do sandwich but better, right? But now Flashbot's like new paradigm is like we have our own like layer 2, and like we do intent matching where like instead of like just like using it for sandwiching, we let you like instead of using a sandwiching where you, like you can bid for block space, you can basically like people can have like like instead of like only bidding for block space, people can just have intents, which is like a very abstract term, which is like, hey, like I want to go from state A to state B, and like I want someone to do it for me. I don't want to figure out the path to like go from A to B. And then MEV searchers will then let you go from state A to state B, and they will be able to arbitrage that from like basically your state transition is what the MEV searchers will like find the most optimal path to execute and then arbitrage that.
And also, if I understand correctly, like, so even if you do make a change like this at the Ethereum protocol level, like Flashbots is going to evolve from more like cross-chain, like intents and like finding opportunities. Like, okay, you want something to happen on like you want to move something from Arbitrum to Optimism in the most like the best way or whatever. So then that would be where they would take the profit as opposed to like directly within an Ethereum block.
Flashbots would run their own shared sequencer.
Rewrite the law. Yeah. Very cool.
Okay. Anything else? Last comments, questions, concerns? All right. Oh.
When mainnet, when token.
And that's
All right.
the other people's problem, not me. Just doing research. Source code is there. You can find it, deploy it, whatever.
When token.
Perfect.
Thank you, bro.
Awesome. Thank you very much, Rodney. It was wonderful to see so much engagement with all this as well. I thought maybe this was going to be a little over, but yeah, no, everybody was really happy to see the engagement. So thank you, everyone. Yeah, if you want, there is the PO app. I would appreciate that if people could do it. We put in time and effort, so let's do that. If you have any questions, ask me. I'll be very happy to help you. If you need, the QR codes are up there for. I think everybody here is a part of it. If you're not, yeah, the QR codes to get into the socials. And Nouns Run Saturday at noon. Yeah, so come well, I guess now that like the Christmas is there, Christmas is now at Cole Harbor or at the Cactus Club.
Just in front of Cactus Club.
Okay, just in front of Cactus Club. Yeah, so just kind of you'll find it. But you want to run?
Running club.
Running. Yeah. 5K. So, yeah, and then ZK next week. Yeah, ZK next Wednesday here at 6:30 on Wednesday, and I think that's it. Oh, we've also got this Saturday. There's going to be kind of a busking 2.0. It's called. It's with Coinos. They are going to be hosting a small kind of event here with some music and the ability to use the Lightning wallet. So if you're not familiar with, it's more of a Bitcoin thing as compared to Ethereum, but yeah, a local company here working on some of that stuff. And there's actually a little candy machine back there too, if you want to test that out. If you've got a Lightning wallet, you can send 21 sats and get some candy. So pretty cool. All right, if you can, just fold up your chairs afterwards. Feel free to hang out and mint your PO app. Thanks, everybody. Bye-bye.
How was it?